So in the second example, we have the integral of x times sine of 3x dx. And using our tips from the previous example, and I ended the previous video, I said that if you have any of the integrals in the form of x to the n times e to the power of ax, x to the n times sine of a to the x, or x to the n times cosine of ax, the tip is u is always going to be the monomial x to the n. Your dv is the complicated part, which will either be e to a to the x or one of the trig functions. So with that being said, if you use that tip, our u is going to be x, and our dv is going to be sine of 3x dx. Okay, so you have to find the derivative of u, followed by the antiderivative of sine of 3x. So what is my derivative of u if u is x? It's just going to be 1, and your antiderivative of sine of 3x dx. Well, first of all, what is the antiderivative of sine? Negative cos. Antiderivative of sine is negative cos. So we have negative cos of 3x. But what do you think is going to happen with this 3?
3x squared negative 3 cos.
Not 3x squared.
Negative 3 cos.
Close. Well, you see, if you're dealing with the chain rule for derivatives, then yes, I would have multiplied by 3. But remember, we're dealing with antiderivatives. So instead of dealing with multiplication, we do the opposite, which is division, right? So the antiderivative of sine of 3x is negative cosine of 3x over 3 dx. And I could quickly just show that if you have this integral sine of 3x dx, right, and you're trying to figure out what's its antiderivative here, you have to do essentially a u substitution. You make your u be equal to 3x, and your derivative du is going to equal to 3 dx. But if you look at inside of your integral, you only have a dx. You don't have 3 dx, so you have to move the 3 to the other side. It becomes 1/3. So this is 1/3 of du equals dx. So the new integral becomes 1/3, you could pull it out, of sine of u du. But then when we integrate sine, we said that the antiderivative is negative cos. So it is 1/3 of negative cosine of u plus c. But then you replace your u with the 3x, what it was defined as before. Right, so it's exactly the same thing. But the shortcut is now that since you're dealing with antiderivatives, instead of multiplying by that constant multiple coefficient of x, you divide by its coefficient. All right. Okay, so now we set up our integration here. We have u times v that goes on the outside. So it's x times negative cosine of 3x, all divided by 3, minus the integral of v times du. So if I take v times du, all we're essentially going to get here is your negative cosine 3x over 3 dx. I made one silly typo. I should have said 1 dx here. Oops. All right. So it's negative cosine 3x over 3 dx. Now, if you look at inside your integral, do you think we have to use integration by parts? No. Here's why. Look at your cosine function. Your cosine function only has a constant multiple of negative 1/3. It's not being multiplied by a variable term anymore. So essentially, you can pull the negative 1/3 out of that integral and just integrate cosine 3x. I'll just clean up the first piece. So the x, I can stick that in front of the negative sign, right? So that would be negative x cosine of 3x over 3. Now, with my integral part, I said I'm pulling out the negative 1/3. So what happens when I pull this negative 1/3 out and I have a negative sign right there? It becomes positive. So we're going to have plus the integral sorry, plus 1/3 of the integral cosine 3x dx. All right, I just gotta integrate this piece now, and we're about done. So what came before, I'm just rewriting it. We have negative x cosine of 3x over 3 plus, well, we have 1/3 of the antiderivative of cosine. So what is the antiderivative of cosine? It's going to be sine, so it's going to be sine of 3x divided by 3. Very good. So it's the same thing with the sine function I showed earlier. You can say the same thing about cosine. You'll have sine of 3x divided by the coefficient of x, which is 3, plus c. And you do one last rewrite. So when I'm doing this problem, I do a lot of rewrites as I go along. So 1/3 of sine of 3x over 3 will now just be sine of 3x over 9 plus c. Any questions? Yes, what, in the previous one? Probably no. I mean, by hand maybe, but on my lab, no. My lab might say simplify your answer. I think that's a question your professor can answer. For me, I mean, that's fine. Like, you know, if I were to throw some really large numbers at you, like let's say this was, you know, I don't know, 82, and this was like 73. I wouldn't ask you to multiply 82 times 73 on the exam, right? I wouldn't ask you to, that you know, something like that. But for this, I think it's manageable. It's manageable. All right. Do you want to see an example a little bit more extreme where I use a different method, not necessarily integration by parts? Huh? We could, but let me just show one more. I'll show one more, and then I'll pause this video. Everybody has this, or it's still copied? Yeah, still recorded. This is the second recording now. Yeah.
You can use what you did in there for this.
What do you mean? That's what I'm going to show you now. Yes, that's right. The only reason why it will work is because, again, look at your u. Your u was a term of x to the n. So if you keep taking repetitive derivative of x to the n, you essentially get to 0. So that's why it works.
One more thing for the antiderivative of dx in the beginning.
Uh-huh.
I thought it was the variable n plus 1 over.
No, because it's inside of the cosine function. So you have to use a u substitution for that. Yeah. If it was just 3x, then power rule works, but it's inside of the cosine function, so you had to use a u sub. All right, let's look at one a little bit more crazy. So this is my third example, and I'm gonna use a different method. Now, let's say if I had the integral of x to the power of 5, x to the power of 5, times cosine of 2x dx. Now, the power of your monomial here, x to the 5th, gives you an idea of how many times you have to use integration by parts. Since the power was 5, it would imply that you essentially have to use the integration by parts how many times? 5 times. Now, do you want to use integration by parts 5 times? Not with an example like this. So what you essentially do is there's something called Tablar's method. Huh? Yeah, you can split it. Yeah, you're creating essentially a table. So here's how Tablar's method work. If he doesn't give you a power this crazy, that's fine. If you use it as x or x squared, that's fine, because it's really simple. But if it goes higher than, I don't know, 3 or whatever, the Tablar method always works.
No, I'm saying, like, usually if we use
It depends on the power.
No, I'm saying, if we use Tablar method, he has to accept it, right?
It depends on him. You have to accept it. I'm just giving you my heads up. If the power is large, use Tablar's method. But if the power is manageable, like to the first power or the second power, just use integration by parts.
I mean, I can only assume if the answer is correct.
Yeah. All right. So your table consists of 3 columns, Tablar's method. The first thing is the alternating signs. And the second thing is going to be u and its derivatives. And the third is going to be your antiderivatives, which we call our dv's. So our first sign is going to be positive because if you look at inside your integral, are there any negative terms there? No. So the first term is going to be positive. Our u, based on our tip, is x to the fifth. And our antiderivative is going to be cosine of 2x. All right, so let's just get our derivatives first. What is the derivative of x to the fifth? 4x to the, 5x to the fourth, thank you. 5x to the fourth. The next one. 20x to the third. 60x to the second. 120x. 120. And then lastly, what is the derivative of 120? 0. Very good. So how many terms do we have here? Well, including the 0, it's 7, right? 7. All right, so what we're going to do here now is write out all the alternating signs. So I go back to the first column. So it's minus, plus, minus, plus, minus, plus. All right, now in the third column, you have to take the antiderivatives. All right. So again, what is your antiderivative of cosine? Sine. So we have sine of 2x. But remember, what do you do with the 2? Do you multiply or divide? You divide. So this is sine of 2x over 2. So this is the only part of Talbot's method to be careful with when you get these fractions, right? Okay, now what is your antiderivative of sine? Negative cosine, so it's going to be negative cosine again. Well, it's just going to be, we're back to cosine again, so it's negative cosine of 2x. Technically, it would have been divided by 2, but since we already have the 2 on the bottom now becomes 4, okay? Originally, there was a 2 there, so when I bring down another 2, 2 times 2 is 4. Okay, now we go down to the fourth row. Antiderivative of cosine. Careful. Is sine. But because there's a negative in front of it, it is going to be a negative sign. So it's negative sine of 2x over what number? 8. Very good. Now we do it again. Now the antiderivative of sine is negative cosine, but since there's a negative in front of the sign, it becomes positive. So it's cosine of 2x divided by 16. Next term, what do you think is going to be? Of over 32. Sine of 2x over 32. And then lastly, what will be your last term? Okay, there you go. All right. So you can sort of see the pattern here, right? Because the sine and cosine, the derivatives go in the sign. It's just that the signs are different. All right, now here's how you combine your terms. The way that tabular method works is that you go straight across, then down 1. Straight across, down 1. So I start with the positive, I go straight across, and then I go down 1. I go straight across, down 1. 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 If you notice, I don't need to go straight across again with the plus 0 part, because when I do 0 times the antiderivative of negative cosine 2x over 64, whatever that is, that's just going to be 0. So that when you end at 0, that's it. The game's over. All right. Now just be careful with your signs. So what we will have as an answer is going to be a lengthy one. I might have to make this font size a little smaller. First term would be x to the fifth times sine of 2x over 2. So the x to the fifth, I could keep that in the top of the fraction part. So I'll say x to the fifth times sine of 2x, all divided by 2. Now I move down to the next one. So my next term would be negative 5x over 4 times negative cosine 2x over 4. What happens to your negatives? the two negatives turns into a positive. Okay, so we have plus 5x to the fourth of cosine of 2x over 4. Now we go down to the next row. It will be positive 20x cubed times negative sine 2x over 8. So the 20x cubed, I can leave it in front of the sign, and I can pull the negative out. Right? So it's going to be minus 20x to the third cosine of 2x over 8. Now we continue again. You'll have now negative 60x squared times cosine of 2x over 16. I'm sorry. Then we go down again. So we have 120x times sine of, so I ran out of room here, so I had to go this way now. 120x of sine 2x over 32. And then the last one will be two negatives there, negative 120 and negative cosine 2x. So that's positive 120 cosine of 2x over 64. And then lastly, plus c. One thing that you could have done here in this problem as well is simplify the fractions, right? You could definitely simplify your fractions here. Yeah, have a question? Wait, sorry. Oh, yeah, you're right. It's sine. My bad. Thank you. Let me fix that. So yes, it should have been 20x cubed times negative sine. So the negative sign, because the negative sign could stay the same. It's just the sign has to change. All right. Yes. So you can definitely simplify the fraction terms, like 20 over 8, 60 over 16, 120 over 32, 120 over 64. But for the purpose of this example and time constraint, I won't simplify.